let's go ahead and do this example. I'm going to do part of it as an example. The other part of it you're going to do as a practice. So it starts out with the coordinates of a bird flying in the xy plane are given as these two functions, and then it gives us the parts of the function. So x is equal to 2.4t, y is equal to 3 minus 1.2t squared. First thing it wants me to do is sketch the path of the bird from t equals 0 to t equals 2. And so in order to sketch this path, there's kind of two ways we can do this. The first way is we can just kind of plot a few points and then give it a sketch. So if I plug in time 0, I find out that I'm right here. So at t equals 0, we're going to start at 0, 3. And then I can plug in 1, and so I can go, okay, at 1 second, I get 2.4, so maybe I'm like over here somewhere. And then I'm at this point. So at t equals 1 second, I end up at 2.4, and if I plug in 1 second here, I get 1.8. And then if I go to 2 seconds, so maybe I'm over here now, t equals 2 seconds, and I plug 2 seconds in, I'm now at 4.8 and negative 1.8. And so I've kind of plotted it, and I say, okay, well, this thing's going to kind of follow this path. That's its path it's taking. Now, some of you might see these two equations and say, oh wait, this is a parametric. And you go, okay, I can solve this equation for t and substitute it in here. And so I end up with a function that looks like, let's write it down here so we save ourselves some space. Y is equal to 3 minus 1.2 times x divided by 2.4 squared. And so I see, oh, it's an x squared, so it's a parabola. It's a negative x squared, so it's a downward caved parabola. And at x equals 0, y equals 3, so that's where our vertex is. And I say, oh, nice. So that's a downward facing parabola. The only thing you would have to do if you wanted to do this sketch for the first 2 seconds is you'd have to plug in 0 seconds and go, okay, I start at x equals 0. And at 2 seconds, so I go to x equals 4.8. And so you would sketch this graph from x equals 0 to x equals 4.8. And you would get this same curve. All right, so go ahead, pause the video, and go ahead and do the practice section, which is the second half of this question just below there. And we'll be right back. All right, we're back. And so I went ahead and I changed this position function. Instead of just showing the components like this, I put the components in an I hat and j hat. This way it'll look a little nicer when I write my equations. It doesn't mean that you can't have like a Vx and a Vy. I'm just writing it as I hat and j hat here. So we're going to go ahead and take the derivative. So we got 2.4. Now if you want to include the units in here on these coefficients, you can. So this would be like 2.4 meters per second I hat, plus take the derivative, I get negative 2.4. And this would be meters per second squared times t. So meters per second squared times seconds gives me meters per second j hat. I prefer to write my units at the end with time in seconds, of course. Take the derivative again to get your acceleration function. And so we end up with 0 in the I hat, so you don't really need to write anything there. You could just leave it blank, or you could write 0 I hat, that is fine. Negative 2.4 meters per second squared j hat. Since it's a constant, I'll put the units in there. All right, now they also want you to then go ahead and write or calculate the magnitude and direction of the velocity and the acceleration at a specific time. Specifically, was it 2 seconds they asked you for? All right, so you need to say, okay, I need the velocity at 2 seconds. You can plug in your information. You see you get 2.4 I hat plus negative 4.8 j hat. Go ahead, draw those two components, and then you need to go ahead and find the magnitude and the direction. So 2.4 times 4, or 2.4 squared plus 4.8 squared gives you this, which comes out to be 5.4 meters per second at, take your inverse tangent of those two, give you 63.4 degrees. And then we just need to, of course, give a direction on this. And so we're going to call that clockwise of the positive x-axis. For the acceleration, it's a little bit easier just because there is no time involved. So it's a constant and it's only in one direction, so it's 2.4 meters per second squared along the negative y-axis. All right, and I think there was one more on there. D says sketch the velocity and the acceleration vectors at 2 seconds. And at this instant, determine if it's speeding up, slowing down, turning directions. So I'm going to take these two and I'm going to draw those two. So I have my velocity that looks like this, and I have my acceleration that looks like this. Now, I'm going to go ahead and break that acceleration vector into components for us here. Components that are either parallel or perpendicular to the velocity. So part of the acceleration is parallel, part of it is perpendicular. So this component of the acceleration right here is in the same direction as the velocity. So this is telling me that it is speeding up. If acceleration and velocity are in the same direction, speeding up. If they're in opposite directions, slowing down. This part of the vector is telling me that it's changing directions. And so it would be turning to the right as it was moving. So this is showing me a change in direction.